Okay. So we've been talking a lot about FFT, and somehow we may have lost sight of AX equal to B. Because we're not saying all we're going to do is AX equal to B all the time, every day. Okay, AX equal to B. And remember, the AX equal to B we're thinking about really comes from that. So let's go ahead and think about that problem. Okay? Stream function solve. At this point, if we're going to do it, what we have available to us is a set of techniques. The fastest one we can guarantee is the LU. We're going to pay order n squared to get that. Okay? So let's talk about what else we might be able to do. Now that thing here is 2 derivatives in x plus 2 derivatives in y is equal to omega. And what we're going to do now is we're going to Fourier transform in x and then Fourier transform in y. Okay? So the hat will be the Fourier transform in x, squiggle, or tilde will be in y. Okay? So let's Fourier transform first in x. By the way, x and y are independent, so when you take an integral with respect to x over all space, the y variable doesn't care at all. Okay? So when we take the Fourier transform of this side and that side, these two, right, are two added functions. It's an integral, so I can separate them. So you have then psi xx plus psi yy is equal. Now, the y derivatives don't matter. I can interchange the integral and the Fourier transform in x because y is an independent variable. So this becomes psi hat yy. Fourier transform in x, I pop out an ik squared. So this is I squared is -1. So I get a minus, let's call it kx squared. That's what happens when I Fourier transform in x. Now, I'm going to Fourier transform in y. That's just a constant. This is giving negative kx squared, Fourier transform hat tilde. Just means it's Fourier transform in x and y. Plus, what's the Fourier transform in y of 2 derivatives from y? Pops out an iky squared. So it gives you a minus ky squared. Boom. And then, if you notice, then I have the following. There it is. If I want to solve this problem, I Fourier transform my vorticity field in x and y. Divide by kx squared plus ky squared. Put a minus sign there. And then inverse Fourier transform. And I'm done. It's n log n in, n log n out. As advertised, n log n. Okay? Pretty sweet. That's what you're going to do. And by the way, if you want to Fourier transform in 2 dimensions, here's the command. Simple as that. Give it a matrix, FFT2, Fourier transforms in x, Fourier transforms in y. It's as easy as that. You want to inverse Fourier transform that thing? Easy as that. Okay. Here's a problem that we haven't talked about quite yet. But now's a good time to mention it. You have this problem here. And what we're going to do is we're going to assume periodic boundaries. Why can we do this? Well, what we're going to assume is I'm going to have a domain I'm going to solve this thing on. Let's draw it here. All right, I'm going to go look in some domain. here's my vorticity. I'm going to look in here and some stuff going on, whatever, some vorticity moving around. I want to assume is kind of the vorticity. I'm going to look at dynamics here in the middle. And we're going to say that the boundaries are way off at the edges. And so you can think of this as sort of not really impacting what's going on in the middle here. This is one way to think about it. Okay? Another way to think about it, is, which we did in class last time, is suppose this pile of vorticity moves over to here. Where's it going to show up? Through over here. So you think about that, my cylindrical world, remember I drew? That stuff would go around, right? So that's possible. So we say let's work for that for now. Part of the reason I want to work with this for now is because I want to use the Fourier transform. I want you to use the Fourier transform. Okay? Now, this has practical implications for us. In particular, let's go ahead and look at this equation here. Suppose I find a solution. Okay? You suppose you get a solution to this thing. Is that a solution? I'm going to take two derivatives. What's going to happen to that constant when I derivative it? It's going to go to 0. Uh-oh. How many solutions do I have? Infinite number. I can pick C to be anything, right? I could pick C to be, everybody agree? Me, Nathan Kutz, right now can pick C to be square root 3 if I want to. You agree with that? And it's still a solution. Anybody can pick a different choice here. I have an infinite number of solutions. By the way, here's the problem with that. When we solve AX equal to B, what do we really want? We want a unique solution out of this thing, right? Normally we say, in fact, what happens when you have AX equal to B? The only time you worry about this is if the determinant of that matrix A is 0. Because if the determinant of that matrix A is 0, it means two things, one of two things. Either there are no solutions, or there's an infinite number of solutions. So you see, by picking periodic boundary conditions, we in some sense have kind of dealt ourselves a little bit of a blow. Because we just made this matrix singular. Right? Everybody good with that? I mean, not good with making matrices singular. That seems like kind of a bad form. So we have to figure out a way to deal with this, though, mathematically, right? Because if you go here and you could say, hey, I'll go ahead and take that matrix that I make there and just do this. You remember that big matrix A? This matrix here has a determinant which is 0. So when you do this, you're in trouble. Okay? Yeah?
Plus CX plus BY, is that?
Yeah, you could do something more general, if you like. Yeah. But this is a problem. And so you've got to figure out how to desingularize the problem. Okay? So we're going to spend some time talking about that. But the simplest thing to do is to say, hey, how about if at one point in my domain, maybe there, I'm going to force psi to be something. K, some constant K. All of a sudden, what does that do? It enforces this constant. By doing something as simple as this, changing one component of this large matrix to a fixed value, the matrix A is no longer singular. If you do not do this, you have an infinite number of solutions. Okay? By the way, when you Fourier transform, it doesn't tell you anything. Here's the other thing that should bother you. Wait a minute. If I have an infinite number of solutions, I'm just pinning it. It's not going to. Wait a minute. I have an infinite number of solutions. Hey, by the way, how are the stream functions related to velocity? Isn't velocity what you're after? Isn't it something like this? I can't remember. Anyway, that's probably wrong. So don't quote that there. But the point is, and by the way, so if you think about it, the stream function is meaningless. It's the derivative of the stream function that means something. So an arbitrary constant still doesn't matter. doesn't screw you up. By the way, if you put in cx plus d, yeah, that x makes a big difference there.
Okay, you have C naught. How do you know it's not plus X?
We'll get to that. Okay? So, but the point is, when you do this, you have to find a way to desingularize. Once you do that, you've removed that. You don't have anything. It's now fixed. There's a unique solution. You don't get any of that stuff in there. And you don't care because at the end, you've made up some parameter C that you're going to take a derivative of anyway, and you're good. Okay?